guys, welcome back. We are going to talk about two things today, or tonight, I guess is when you're actually watching it. We need to talk about equilibrium. Oh yeah, we're not actually done with it. Nice try though. So we're going to talk about equilibrium when we're looking at complex ions, and we also want to look at geometries. What are the shapes of those complex ions? So those are the two things. We're going to start with some stuff we know, and we're going to go with equilibrium, and we're going to introduce a new KEQ called KF. So, you know, previously we've had KC, we've had KP, we've had KA, whoa, I can't write apparently, KA, KB, KW, they're all just KEQs, right? Now we have a KF, and a KF is the formation constant, that's where the F comes from, for forming a complex ion. From the metal ion and its ligands. So the equilibrium that we're talking about here is, for example, if we were interested in this particular complex ion, you might ask yourself, do I know what the name of that is? So dicyano silver 1, although you don't really need to say the 1 with silver because it's always 1. But we're talking about the formation of this. So the equilibrium, or the equation that you would draw for the equilibrium, would look like this. The silver ion plus 2 cyanide ion at equilibrium in order to form the complex ion. So with a KF, the complex ion is always on the right-hand side. As we look at this then, this just is an ordinary equilibrium, and so we can write a KEQ, but we're just going to call that KF for this. So the KF for this particular equilibrium would be, once again, products over reactants, and the concentration of silver ion times the concentration of cyanide ion squared. And just to give you an idea, what's unique about these KFs is that the KF for a complex ion is often huge. So like the KF for this is 2 times 10 to the 20th. So think about that. If this is that huge, that means this number is enormous, and these numbers are very, very small. So essentially, many of these complex ions really act as though they go to completion. They don't. There's, you know, still a molecule or two left of the reactants, but very, very few, because this number is huge. And this is certainly not the biggest KF you can find. There's a table of KFs in your book. Look at it. There's some really large numbers. So I just want to do one example problem. It's really, we're not changing anything. Equilibrium has not changed since the last several chapters, but let's just do an example. And here's a question. How much cadmium, actually let's make it how much cadmium ion, because that's really what we're talking about, is actually complexed when dissolved in 0.20 molar cyanide ion solution. And so in order to answer the question, what we're going to really do is we're going to find the ratio, not ration, that's silly. Find the ratio of, we'll find out what is the concentration of this to the uncomplexed ion. Good rule of thumb, I know I mentioned it in one of the classes, but not necessarily both. This is an example, and just to kind of go along, sometimes the question is, well, how do I know how many ligands are going to attach to my ion? And one of the things I said is a general rule, but you'll see that it doesn't obey it in this case, that's why I'm bringing it up, is that a general rule is if you are not told, you could double the charge, oops, it actually does follow, I'm not even thinking, double the charge of the metal ion to determine the number of ligands. And I was looking at the ligand, but in this case, the cadmium ion is +2. So it's not uncommon to find there being 4 ligands, double that charge. And in this particular case, you can see that, in fact, there are 4 ligands. Again, general rule, not always true. Sometimes you're told otherwise. That's fine. You can completely accept that to be true. But I do need to give you the KF for this. And for the cadmium and cyanide complex here, it's 2 × 10 to the 18th. So a lot of our same rules here hold true. I mean, they all hold true. We can write a equation, right? Cadmium plus 4 cyanide ion. This is really essentially going to completion because that number is so big. But we're going to go ahead and find that. And we can write a KF expression for that. So the cadmium, cyanide, all that good stuff, over the cadmium and the cyanide. And, you know, certainly we could do an ice table for this, but in this kind of problem, we could probably avoid the ice table just because of what the question is asking. Okay, but it certainly, you know, our next step would be to do an ice table, and sometimes we have enough information that we should. But I want you to notice what we're being asked for. What we want is this ratio. So let's solve it for that ratio. So then if I take the KF times the concentration of the cyanide ion to the 4th, that gives me the ratio that I'm interested in. And since, if I go back to the original problem, I want to know when it's dissolved in this concentration of Cn-, how much exists. Well, that's this number. So I can actually make my life really simple because this is 2 × 10 to the 18th. This is going to be that 0.2 molar to the 4th, and that is equal to 3 × 10 to the 15th. So ratio-wise, if that's this concentration over this, that's like 3 × 10 to the 15th over 1. That means for every one of these, I'm going to have 3 × 10 to the 15th more concentration of the complex. So that's how far over to the right this is shifted. So not any different, just really the only thing that's being introduced here is the idea of the KF and how you write that formula. All right, the other thing I said, there were 2 things today. One was the equilibrium, the other is the geometries, and this is not difficult. I just kind of need to show it to you. And I'm going to just make a little table. But as those ligands attach to the central metal cation, they attach in a specific shape. So we're going to take a look at the coordination number. I'm going to give you an example, and then I'm going to show you what that shape was to look like. So, simple, coordination number of 2. An example of that might be this, diamine silver. And very simply, this is the center, that's the central metal cation. The ligands, very often, just like we've done before, kind of get apart from each other. So the shape here, the metal goes in the middle, the ligands go as far apart from each other as possible. The shape of that complex ion is linear. Coordination number of 4. Now there's 2 different shapes that go with a coordination number of 4. One of them doesn't happen as often. We'll tend to find it with zinc and cobalt and a handful of other transition metals. The other is much more common. So here's an example. Zinc surrounded by 4 things. That's why it has a coordination number of 4. And this is what we actually, this is the shape that we actually expect based on our past knowledge of molecules with 4 things around them. That essentially they form a tetrahedral shape. Ligand, 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 ligand. So with a tetrahedral shape, we find that primarily with zinc and cobalt. One thing you should be aware of is if you have an example where, I'm just going to kind of write this down, you know, where it's perhaps 3 ammonias and a chloride ion, so then this becomes +1, but the zinc is still +2. It does change things in terms of isomers. So we'll make these ligands happen to be the ammonias. No, actually, you know what? I need a different example. My apologies. Let me write out a whole different example. We'll keep it with zinc. I'm going to make this one fun. NH3 BrCl. I'm not putting this in a good order. Water, and that actually has no charge, because this has a negative, this has a negative, this is +2, so there actually is no charge associated with this one. The reason I bring that up is because if you have that particular one, I'm going to just kind of write these in, NH3, Br, and a water are my ligands. If all 4 of the ligands are different, we actually can get an isomer out of it. And that isomer would be the mirror image. So let me try to draw the mirror image of that. So notice here we've got that mirror image. If you have 4 different things, it's possible to have what's known as an optical isomer. And an optical isomer is when you have 4 different ligands and their mirror images. They are actually different molecules. Many of you in Chem 1 had learned about optical isomers and built it rather than with ligands, but with just 4 different atoms. But the same is true if there are 4 different ligands. Okay, another coordination number of 4, which is more common, is a slightly different shape. And an example of that might be copper, with 2 ammonias and 2 chlorines. And more commonly, it forms this shape, which is called square planar. So it literally is all in a plane. It's not tetrahedral. And this lends itself to 2 isomers. And this example will illustrate that pretty well. Because you could have, for example, the 2 ammonias that are found in there being next to each other, or you could find the 2 ammonias, or the 2 chlorines, however you want to look at it, being opposite each other. This is known as a cis isomer. Cis means next to. These guys are next to. This other one, when it's opposite, is trans, and trans means opposite, and we've got ligands opposite each other. So this one literally could be called, in this case, cis diamine dichloro copper. This is still copper 2, whereas this one would be transdiamine chlorocopper 2. All right, the last one to finish us up, coordination number of 6. So an example might be cobalt with 4 ammonias attached and a chlorine. This one doesn't have a charge either. And when 4 things try to get around that central atom, they make an octahedral shape, which shouldn't be a surprise to us. So octahedral, metal, ligand, and then square planar. We learned about octahedral with atoms, or I'm sorry, with molecules. This is no different. Some of that same terminology applies, like equatorial and axial positions, just in terms of referring to those things. And there are also, just as in with the molecules, some different kinds of isomers that could exist as well, such as, we'll put the chlorines in the axial positions here and the ammonias in the equatorial positions, versus if I put rather than having the chlorines opposite each other, maybe I'll put ammonia across there, and then I'll put a chlorine in one of the equatorial positions. So here, they're opposite each other. Here, they're next to each other. Opposite is trans. This is the trans version of this isomer. This is the cis version. And the reason that that's important is because in an isomer, it changes the properties. These are two different molecules. They have different properties. So, just as an example, there is something known as cis platinum NH32Cl2. This particular molecule has anti-tumor properties. It actually can make tumors grow smaller. Turns out if you have the trans version of it, the trans version has absolutely no anti-tumor properties. They are different molecules. They exhibit different behaviors and properties. So that finishes up today. I know that was a lot of stuff, and then I will see you in class tomorrow.